Okay, so we've just looked at what a probability distribution means in generic terms, and we've talked about discrete and continuous probability distributions. And I now want to look at some specific examples. We can cover this fairly briefly. There are many probability distributions. We couldn't cover all of them. There would be no point in doing so. All I want to do is draw on some examples and interpret them with respect to real world phenomena, just to make this idea of a probability distribution more concrete. We may look at these probability distributions in a bit more detail when we meet in class. And as you'll see in the notes, I've included some R code to generate probability distributions in the statistical software R. So that will allow you to explore some of these in your own time. Okay, first I want to deal with discrete probability distributions. And the first one that I want to talk about is the simplest in a way. It's called the discrete uniform distribution. And this is what the probability mass function would look like in a specific case. Now, this is a probability mass function for a discrete random variable, integer random variable. It has a single parameter n, and the PMF has this specific analytical form. This is the equation. It's simply 1 over n. So this is a model that assigns equal probability to each of the n possible values that the random variable can take. And in the example above, n has been set equal to 6. And the reason I did this is just to show you what the PMF would look like in the case of throwing a dice. So the dice can take the integers 1, 2, 3, 4, 5 up to 6, and the probability of throwing each of these is always equal, which is why this equation generates equal probabilities. Okay, so yeah, we want to throw a fair dice. The set of outcomes is given here. This is the support of the PDF. As long as the dice is genuinely fair, the probability is always 1 over 6, as shown in the plot of the PMF. Okay, so that's a discrete uniform distribution. A second very well known distribution is the Bernoulli distribution, and this is the distribution for binary random variables. It has a single parameter p, and it's the distribution for a binary outcome in which you're looking at the success in a 0-1 trial with the probability of success being captured by this parameter p. So this is a distribution that would work for a coin toss. You know, is the coin going to land heads 0 or tails 1? Now in that case, if the coin was fair, the probability would be 0.5, and the distribution would look very much like the uniform distribution where n equals 2. In fact, it'd be the same. But this distribution also extends to cases where the coin isn't fair, as in the example above, where the probability of success in this case equals 0.2. Probability of failure, or probability of obtaining 0, let's say, is 0.8. Probability of obtaining 1 is 0.2. And so, you know, when x equals 0, this reduces and you just get 1 minus p to 1 minus x, which is 1 minus p, yeah, so 0.2. And when x is equal to 1, you just get the probability of the power of 1. Okay, so that's how it works. And as an example of a Bernoulli distributed random variable, a COVID test is to be used on the population. The set of outcomes for each test is 0, 1, where 0 indicates we get a negative test result and 1 indicates a positive test result. If the probability in the population of obtaining a positive test is 0.2, then the probability of obtaining a negative test is 0.8, and that is how that distribution would look. Okay, binomial distribution. I mean, what I'm trying to do in showing these distributions is just illustrate that for different types of experiments, for different processes, the distributions look different and they have different formula. Okay. The binomial distribution is a distribution for a series of independent Bernoulli trials, so a series of 0-1 trials, and it has two parameters, n, which indicates the number of trials, and p, which indicates the probability of success in a trial. So this is a distribution again for integer values. It has this form here. So the binomial coefficient, if you don't remember what that is, please look up the mathematical text that I've written to go along with this course. Binomial distribution times p to the power x times 1 minus p to the power n minus x. And to give an example of binomial, let's say we have a multiple choice exam and each of 20 questions has 5 possible answers. Now, if we go in with sheer ignorance, the probability of guessing the right answer is 1 over 5, or 0.2. So the random variable corresponding to the total number of correct answers, assuming that each question is answered by guesswork, would have a binomial distribution where n equals 20 and the probability of success equals 0.2. Okay, other discrete distributions. This distribution, the geometric distribution, which is a single parameter p, is a distribution. It's called a discrete waiting time distribution. So it's a model for the number of 0-1 trials that we conduct until the first success is obtained. The single parameter again relates to the probability of success in each trial, and the distribution is for non-negative integers. And that's how it would look. Sorry, it might look like this. In the above example, we have x equal to 1. So, to give an example of a waiting time distribution, disruptions on the northern line due to technical failure occur with probability p equals 0.01. We observe trains running on the line, and the random variable x corresponding to the number of trains that will run before the first failure has a geometric distribution with parameter p. Okay, so it's a waiting time distribution, waiting for an event, or in this case for a failure. Next in discrete distributions, this is actually quite an important distribution, and many of you will have heard of it, and it's called the Poisson distribution. And it has this shape here. Again, it's for a discrete random variable, a non-negative integer, and it has a single parameter called the rate parameter, and it's the rate of occurrence of events. This is the PMF. It takes this form here. So this is the single parameter, lambda. And the Poisson distribution is a model for count data. So we often use it in things like analysing accidents, analysing breakdowns, used a lot, for instance, in modelling road traffic accidents. And it's a model for count data that calculates the probability of a given number of events, so number of accidents, number of breakdowns, that occurs in a fixed interval of time or space. So, traffic accidents on a road link, let's say we know that they follow a Poisson distribution with an average rate of lambda equals 1.6 per week. Then we can predict the probability of future accidents. And I've put some R code here which allows you to say, okay, what's the probability that in the next 4 weeks there will be 0, 1, up to 10 accidents? It allows you to calculate those probabilities from this distribution, the Poisson. Okay, that is all I want to say about discrete distributions. If many of you, when you come to do your own research or your own projects or other courses, actually will come across other distributions that I haven't covered here. The point isn't to be comprehensive, it's really just to demonstrate, as I said, different distributions for different types of process. Now we're going to move on now to continuous probability distributions. I'm going to start with possibly the most famous of all continuous distributions. It's called the normal, or sometimes Gaussian distribution, and it's surely the most important distribution in statistics. It has so many applications and so much theoretical value. The normal distribution is important because it characterizes many natural phenomena. So the birth rate of babies, the height of people, blood pressure of people, the height of trees in a forest, the growth of plants in a field, all of these natural phenomena tend to follow our normal distribution. And it has this shape. It's a kind of bell-shaped symmetric distribution. Its support is the real line. It's governed by two parameters, mu and sigma. Mu is a measure of the centre of the distribution. It's actually called the expected value of the mean. And sigma, or sigma squared, has got to do with the spread of the distribution, and that is called the standard deviation of the variance. The density function takes this form here, and we interpret the normal distribution as a probability model that reflects the observed empirical behaviour of data samples, or many data samples, in the real world. Now, remember that when we calculate probabilities from a probability density function, when we're dealing with a continuous random variable, we have to talk about probabilities in terms of ranges. So the probability that random variable x takes a value between a and b is the integral of the PDF over the range a and b, which, so for instance, on the left hand side here, let's say we're interested in x taking the probability that x takes a value in a small range around 0, then that might look like this green area there. That would be the integral, the area under the PDF around some small region around 0. The second diagram shows a different thing. We're interested in x taking a value greater than some specific value of x, in this case 0. That's the integral of the PDF from x up to all the values potentially that the random variable x could take. So over here, it's this area under the curve, which in the case of a normal distribution would result in a probability equal to 0.5, because of course the distribution is symmetric. So, governed by two parameters, and of course the parameters are important. These parameters define the family of distribution. But when we set specific values to them, that changes the shape of the distribution for one specific sample or instance, let's say. So for instance, here we have the red distribution. The red normal distribution has a mean of 0 and a variance of 1. The blue distribution has the same mean, so the central tendency of a distribution is in the same place, but it's got greater variance. And that's caused the distribution to shrink in height and become wider. We increase variance again, this time up to 5, and again it causes the distribution to become smaller in height, shorter and fatter. And if we change the mean, so we shift the mean, the location parameter it's called, we shift the mean to 1, that would shift the distribution from the red position out to the green. Variance is the same, but the mean has changed. So that plot just illustrates how parameter values change the location and shape of the distribution within the normal parametric family. I mean, as I said, and just to emphasize, the normal distribution is absolutely key in statistical theory and practice. It plays a central role for three main reasons. First of all, although it might not look it with this equation, it's actually analytically tractable, and it's easy to do mathematics with this form. As I said earlier, the normal distribution is prevalent in nature. It describes the observed empirical behaviour of many types of experiment, many processes, many random variables, either exactly or approximately. And it can be used to approximate a great variety of distributions in large samples. And this is known as the central limit theorem, very important theorem in probability and statistics, and we'll talk about it later in the course. Now, the normal distribution is symmetric around its mean, and for that reason, the mean and the median are equivalent. You can see it's symmetric. 68% of observations, well, this is some notes that characterize the normal distribution. 68% of observations in the normal distribution fall within one standard deviation of the mean, and 98% of observations fall within 2 standard deviations of the mean. So a very important continuous probability density function. We'll look at some other ones. Again, we'll do this briefly because we're actually kind of repeating a lot of the distributions we had in the discrete case, but we're looking at them for a continuous random variable. First is the continuous uniform distribution. This is a model, again, assigning constant probability to a density, probability density on a region. So remember, in the discrete case, the density function was just 1 over n, but we're no longer dealing with discrete random variables. We have to talk in terms of ranges, and now the density function is 1 over b minus a for some range, trying to work out the probability that x falls in the region a to b. But you can see here the probabilities for the regions are the same. So I've got an example here. Heathrow Express trains have a 15-minute headway. That means they arrive, when one leaves, the next train will arrive 15 minutes later. If I arrive randomly at the platform, the probability of having to wait to the nearest number of minutes is the same. It's always 1 over 15. And this is because wait times are uniformly distributed in that interval. So we can calculate probabilities for intervals using integration. What's the probability that random variable x falls between two numbers c and d? Well, we just integrate our PDF with respect to c and d, that interval, d to c, and that gives us that expression there. So in our example, to calculate the probability that I will wait less than 10 minutes for a train, I'm going to set d equal to 10, c equal to 0, and using our integral of the PDF, the correct probability is 2/3. Okay, some other distributions. The exponential distribution. This is a waiting time distribution, a continuous waiting time model, but yeah, in this case for continuous random variables for the time between events. Its range is the positive part of the real line, and it has a single parameter lambda, which again is a rate parameter describing the occurrence of events. And this is what the exponential distribution looks like for different values of lambda. And this distribution, to give an example of when a waiting time distribution would be relevant, let's say our bus arrivals have a Poisson distribution with rate parameter lambda. That is, arrivals are essentially random. Then the random variable x corresponding to the arrival of the first bus has an exponential distribution. Its CDF is given by this expression there. And note that the probability that x takes a value greater than x is given by that expression there. And we'll look perhaps at this distribution in the tutorial. Okay, just a few other distributions, and I'll go through these quite quickly because I think by now you're getting the picture that really what I want to emphasize is that the analytical form of these distributions depends on the process we're looking at. The gamma distribution, just another continuous time waiting distribution. This time we're interested in the waiting time until the kth event occurs. Okay, so example, a mechanical component fails in such a way that the number of failures in a given month has a Poisson distribution with rate parameter lambda. If a component is installed at time x equals 0, the random variable corresponding to the time until the nth failure has a gamma distribution with parameters n and lambda. Okay, so it's really as simple as that. Okay, beta distribution, a model for experiments whose outcomes lie in a bounded interval. This is a distribution that's often used to model proportions. The log normal distribution, a distribution for, well, that has a log, it's skewed to the right, as you can see, unlike the normal distribution. And if the log of random variable x is normally distributed with parameters mu and sigma squared, then x itself has a log normal distribution. And the fact that unlike the normal distribution this has a skew, it's not symmetric, can be quite useful in measuring or representing certain types of processes. This is actually a good distribution for things like travel times, which tend to have a long right-hand skew. Okay, I think that's all we need to say on distributions. The central message, as I say, to take away from this is that different types of distribution for different types of experiment or process. Crucially, discrete random variables have got probability mass functions, and there's various different types of those. Continuous random variables have probability density functions, and I've tried to illustrate a few different examples of those in this part of the lecture.